Okay, so in this video, I'm going to talk about how to solve systems of equations, of linear equations, using Gaussian elimination by looking at the following example. So this is a system of three equations, three unknowns, and we want to determine whether it has a solution, and if it has a solution, what that solution is. So the first thing that we want to do is we want to rewrite it in matrix vector notation here, and convince yourself that our system here is equivalent to AX is equal to B, when A is this matrix here, this is a vector X, and this is the vector B. Okay, so in order to solve this, right, we write it in augmented form. So this is my matrix A right here, and this is my vector B, and I'm going to perform a series of row operations that are allowed in order to get it into row-reduced echelon form, hopefully getting to the identity. So my goal is first to focus on this first column. I want to make these two guys 0. And so what I can do is I can first do this row 2 minus row 1. And so I get this, if I add, or plus row 1, if we add them, I get 0. I get minus 1. I get 1. And I get 2 here. Okay. At the same time, I want to make this to 0, and so I can do row 3 minus 2 row 1, giving me a 0 here, right? And then you have a minus 2 times 2, which is positive 4, minus 1 is positive 3, okay? And then finally, you have 3 minus 2, which is, so we're over here, which is minus 6, minus 1, it's minus 7. That should be a minus 7. And you end up, let's see, 7 here, so a 7 times negative 2, that's minus 14, plus 4 is negative 10. Okay, well, I am now happy with the first column, so now I want to work on the second column, right? So the first thing that I do is I want to make this guy a 0, and I can do that by just taking row 3 plus 3 times row 2, which gives me this new augmented matrix. You guys can pause the video to make sure that you actually get that. Okay, so I can now work on this minus 1 and this minus 4 by simply taking the negative of row 2, which gives me positive 1, and then multiplying row 3 times minus 1/4, right, which gives me what I have here. Okay, we're getting there. Now I can make this guy a 0, right, by simply taking row 1 plus 2 row 2, and I can make this guy a 0 by taking row 2 plus row 3, and I end up with this guy, and I just need one final step to remove this guy, and I simply can do row 1 minus row 3, and I end up with the identity matrix, 0, 0, 1, and this is going to be 2 minus 1, 1, okay? So basically I'm done with the row reduction process. Now I just have to conclude what my solution is. So essentially what we have concluded is that this was our original matrix, A augmented with B, is really equivalent to this guy here, okay? And so this guy is equivalent to the identity times x is equal to now the vector 2 minus 1, 1. So if we are to multiply this out, times x1, x2, x3, what do we get? well, we get the vector x1, x2, x3, and that is equal to 2 minus 1, 1. Okay, so we have found our solution. Now we simply have to double check. Okay, I'm just taking the matrix A and our solution x here, and I'm multiplying it out. And I end up, you see, with 7 minus 5 and 4, which is indeed what we wanted, right? So we got our solution. So in the previous case, we ended up with the identity matrix, and that guarantees that there is only one solution, right? But how do we know if there are no solutions or an infinite number of solutions? So we would know that the system has no solutions if when we get it to row reduced echelon form, we end up with a row that has basically zeros on the left-hand side and something that's non-zero on the right-hand side, right? Because essentially this would be a contradiction. It would tell us that 0 times x1 plus 0 times x2 plus 0 times x3 is equal to a, which is not equal to 0, right? So clearly this has no solutions. To know if you have an infinite number of solutions, first of all, you're not going to have the identity matrix. Whenever you row reduce it to row reduced echelon form, right, this satisfies it. Certainly the first non-zero element is a 1, okay, and the first one in every row is to the right of the row above. But you can't reduce this any longer, right? So the first thing to note is if you have an infinite number of solutions, you're going to have a row that has all zeros. And so that means that you can't possibly get rid of this 1, okay? So let's look at what this represents. It represents the following system: 1, 0, 0, 0, 1, 1, 0, 0, 0. Times x1, x2, x3 is equal to a, b, 0. So if I multiply this guy out, I get that x1 has to be a, okay? And then now I'm multiplying the second row times my vector x, I end up with x2 plus x3 has to be b. And then this doesn't tell me anything, right? Because there's no contradiction. So here's my solution. X1 has to be a, and then x2, it just has to be b minus x3. So no matter what I choose for x3, this is going to be a solution, right? So this has an infinite number of solutions. And I would usually write it as x1 is a, x2 is b minus s, okay, and x3 is s, and s can be any real number, right? So it's an infinite number of solutions. As soon as you have one, you have an infinite number.